Okay, so 2.2, tangent lines and local linearity. If you remember in geometry, you learned about the secant line right here that intersects a circle, okay, in two places. We talked about it the other day. And then we also learned that a tangent line is a line that intersects a circle at one point. All right. Okay, and also remember we learned about our trig stuff. We learned about the cosine, the tangent, and how that's the sine and the cosine, so on. But what we're going to focus on right now is we're going to focus on the tangent line to a curve. So we think that a tangent line to a curve intersects the curve at exactly one point. But I want you to look at the figure down below. So if you notice that the one that goes through Q right here, this is not tangent at Q, but look at P. It is tangent to P. It is tangent to that point. If it was tangent to Q, then we would have something that looked something like, oops, that's not it. Hold on, let me erase that. Okay, we would have something that would look something like at this point, it would be a line at that point, right there, just barely hitting the Q. But P is actually tangent to it. So let's move on. Okay. Okay, this is really important. So a tangent to a curve, hence the reason that it's in bold, a tangent to a curve at a point is the line that best models or approximates the behavior of the curve at that point. So this will be referred to as the slope of the tangent line, instantaneous rate of change. Remember IROC? Okay, IROC cannot be, you cannot pick points that are really close to get the IROC. What you actually need to do is you have to do the derivative, and we're going to talk about the derivative in just a second. So, an important thing to note here is that the tangent curve at any given point is unique. So, a function f that has a defined slope at x equals a, okay? So, we have a slope right here at a, has two things in common with its tangent at x equals a. So, the point of tangent c, which is right here, and the slope of the point of the tangent c. So if we wanted to find the slope, we would do this, and this is called the derivative. It's said or read as f prime of a. So take a look at this. Any function with a defined slope at a specific point will have one and only one tangent line at that point. So each point on the curve will only have one tangent line. All right. So let's move on to here, and let me move this down a little bit. Okay, so in the figure below, it says it wants you to use a straight edge, so you're going to want to get a calculator or something, to draw a tangent line beyond the point of tangency in each direction. Okay, unfortunately, I don't have the option to have a straight edge on here, but if I was going to draw a line that is tangent to A, that means it would, oops, let me try to get as specific as I can. It would be something like that. A line that is tangent to B would be, see if I can get it close, right there. And then a line that is tangent to C would be that line right there, okay? They are the lines that are going through just that point. Okay, so if we do the next one, if we try to draw a line through A, we're going to get right on there. A line through C, we're going to get right on there. Now B, I mean, what am I supposed to do with B? I don't even know what to do with B, because I don't know which way to go, because I can go like this way, this way, this way. I mean, all those points only touch it once. That's why there is a problem with that figure. Okay, so if we look at the next figure, again, we've got a problem. Notice this here. I don't know how to draw the tangent line. Should I draw it like that? Should I draw it like that? Like, there's too many ways to draw the tangent line. Of course, I guess I could draw a tangent line at A and a tangent line at C on figure on figure 2, I don't know where to do the tangent line right here at your point of inflection. Kind of freaks me out. I don't know which way to go. And then on A, I could probably do it here, and C like here. All right, so let's take a look at this. So what's going on? So what we're talking about is concavity, corners, and points of inflection. So how does the position of a tangent line in the graph from example 1 relate to the concavity of the function in its model? So if we look at it, when the curve is concave up, the tangent line lies below the curve. So get my pen again, sorry. Below the curve. Okay, when the curve is concave down, the tangent line lies above the curve. Okay, at a turning point, a maximum or a minimum, the tangent is either 0, if you look at that first curve, right, where it goes at the maximum of our thing. If you notice, our tangent line has a slope of 0. It's either 0 or it's horizontal. Okay, now at a point of inflection, concavity changes. So the tangent at a point of inflection is vertical or 0. And at a sharp corner or at a cusp, the tangent line does not exist. At a point on a linear function, the tangent line is the same slope as the line. Oops, as the line. All right, let's keep going. Okay, so it says, in your algebra, what two facts are needed to write the equation of a line? So if you remember, in order to write an equation of a line, we need slope. Oops, sorry. We need a slope, and in calculus, the slope is going to be f prime a, which is the derivative, and we need a point. And in calculus, we call that a at f at a. Okay, so also what we learned when you write equations, when you wrote equations, there were two forms you could write it in. You can write it in slope-intercept form, which is y equals mx plus b. You could write it in point-slope form, which is, if you remember, y1 equals m times x minus x1. Or if we move that around and solve for y, we've got y is equal to m times x minus x1 plus y1, solving for y. All right, so here we go. It says, in calculus, we're going to focus on using pretty much just this form. So using your figure number 1, estimate the slope at each of the points and use this information to complete the table below. So if you go back to that graph that you saw, the number 1 graph, right, figure 1, we're going to take a look at those tangent lines and we're going to estimate the slope. So just by looking at, that's why they say use a straight edge, because you can get a point. So apparently with A, there was a place where there was a point at -5, -5. And then when they found the slope, they were kind of estimating the slope. They found the slope to be 5, just going like up 1 over 1, whatever, or up 5 over 5. So if we did the equation of this, so f at x is going to be equal to, let's just plug it in, 5 times x plus 5 minus 5. So that would be our equation for that one. All right, let's go to B. Let me move this up a little bit. Oops, wrong one. Okay, I'm going to have to move it together. Okay, let's go to B, and let's do B. So At B, apparently there was a point, and it looked like it was at -1, 3. The slope, because it's at the very top, so it's a turning point, so the slope is at 0, right? It's a horizontal line. And so that would give our function that f at x is going to be equal to 3. All right, for our C point, apparently it went through the point 1, 1. The slope was around 3/2. And that would give our function 3/2 x minus 1 plus 1. All right, so let's pull this all together. So we just said, let me get my red, we said since we know that slope formulas and have discovered that the slope of the tangent line will be called the derivative. So the derivative of your function is going to be the slope of your tangent line, which is y2 minus y1 over x2 minus x1. We understand that. We know how to find slope. The only thing that's different is what you should see is this. Our slope is actually the derivative of our equation. So since we know that, we can now write a new equation. Please excuse this black line, but we can write that f of x is equal to the derivative, which is our slope, right, of x minus a plus f at a. Okay, because think about it. Didn't we say this is slope x minus x1 plus y1? So that only makes sense that that would be a and that would be f at a. So this is just writing it in the form, in a calculus form. All right. Okay, so let's take a look at what this says. It says a function f is said to be differentiable at point A, f at a, if and only if it has a defined slope at x equals a. So this is important. It has to have a defined slope at x at a. If a function does not have a tangent at a specific point, then the function cannot have a slope there either. And if you think about it, that's when I was telling you on those 3 figures that where I didn't know where to put the tangent line, they were all point B, because like I didn't really have a defined point there. So why are we using this? Well, here's an example. So say you are you're looking at the revenue at your local theater affected by a small change in the ticket price for a movie. So to do that, we can use the application of the tangent line to a function, which is called the linear approximation. So you've already seen that a curve lies very close to its tangent line. Remember, we were looking at that near the point of tangency right here. And we said if we zoomed in, right? Zoomed in really close, you would see that at that curve, it looks like a linear line. And if you think about it, our tangent line would also look like a linear line. It'd be hard to see which one was which, but that's the property, that's this here. Differential function is commonly referred to as local linearity. All right, so let's see what we got next. Okay, so for this point, you need to go get your calculators. So go ahead and get your calculators, and you want to put in sine x. So we're going to put in sine x. All right, so what I want you to do now, you should have sine x in. So make sure, you know, when you graphed it, you can see the sign. What I want you to do is I want you to go to Menu, Window, and click on number 3, Zoom In. And make sure that your little plus sign there is on the origin, okay? And I want you to click it 4 times. So what's going to happen is you're going to see that your sign kind of looks like a straight line. So with that, it says, can you tell the slope of this portion of the sine curve by inspection of this window? So it appears to have a slope of 1. So what can you say about the slope of the tangent line at x equals 0 on the function y equals sine x? So the slope of the tangent line at x equals 0 is 1 on the function. So that's what we're going to say. We're going to say the slope of the tangent line at x equals 0 is 1 on the function y equals sine x. Okay, so now it says consider the radical function y equals the square root of x. Okay, and the slope or the general derivative of this function at any given value of x in its domain. So they're just giving you the derivative. Now hang in there because we're going to start doing the derivatives on our own. This is the derivative, which means this is our slope. So it says to find the slope of f of x equals the square root of x at 9, all we have to do is just plug it in. So f prime at 9 is going to be equal to 1 over 2 the square root of 9, which is going to give us 1 over 6. So now we have our slope. It says write an equation for the local linearization of f near x equals 9. So if you think about it, what we're missing a point. Well, we know that x is 9, so let's find y. So let's just plug it in. So f at 9 is equal to the square root of 9, which equals 3. So we have a point. We've got 9 and 3, and we have a slope. So y, or f at x, is equal to our slope, x minus 9 plus 3. There's our equation. Now it says using your results from C, estimate the value of 9.1. Do not use a calculator. Well, actually, they mean the results from B, not C. Do not use a calculator. Show your setup. So if we want to estimate the value of the square root of 9.1, right, which means that is our x value, this is what we want to do. We want to say y is equal to 1/6 of 9.1 minus 9 plus 3. So we've got y equals 1/6 of 0.1 plus 3. So it's going to be approximately 3.0166. All right, so now it says graph the function and its tangent line at x equals 9. Okay, so if we let's graph the function first. All right, so oops, let me get my pen again. So our function is f at x equals the square root of x. So at 0, it's 0. At 1, it's 1. At 4, it's 2. At 9, it's 3, etc., etc., right? So let's see, we can do 16, it's 4. So here is the graph of our function. Now, if you think about it, we know at 9, we know what the slope is, and the slope is up 1 over 6. So at 9, our slope is up 1 over 1, 2, 3, 4, 5, 6, or down 1 over 1, 2, 3, 4, 5, 6. So it's going to be something like that. All right, that's our tangent line. Okay, so now it says explain whether your answer to C is an overestimate or an underestimate of the actual value of the square root of 9.1. Justify your answer by reference to the behavior of the graph of f of x at the square root of x. So if you think about this, since f of x, f at x, is concave down, that means that the estimate, let's try this again. The estimate is an over approximation It's an over approximation because the tangent line is above the function. Because the tangent line is above the function. Okay, it says find the true value of the square root of 9.1. So now you can grab your calculator and plug in the square root of 9.1, and you should get 3.0166. Okay, now it says, well, let's go ahead, hold on, let me move it. Okay, it says, would your linear approximation formula also be an accurate tool to estimate the square root of 25? Why or why not? Well, I mean, if you think about it, no, of course it's not going to be a good one because the square root of 25 is way too far away from our 9, right? So the square root of 25 is too far away from the point of tangency. It's outside the local neighborhood. It is outside the local neighborhood. I mean, think about it. It's outside of where we were at. That's what they're saying. All right, I'm done.